This is a question from your textbook, exercise 10.3, question number 11. Barry has been contributing $1,000 at the end of every 3 months, that's quarterly, into a retirement fund for the past 10 years. He decides to stop making payments and to allow his investment to grow for another 5 years. And if money earns 8% compounded semi-annually, how much interest would he have earned over the 15-year time period? Well, in order for me to attack this problem, I am certainly going to make a note of the fact that the interest rate is 8% compounded semi-annually, which means it's 4% every 6 months. Now, I don't like solving any financial problems unless I make a time diagram so that I can get some perspective on the problem. So in this case, what we have is Barry making contributions to a retirement fund for 10 years. So for 10 years, he's making 10 years worth of deposits at a rate of $1,000 per quarter. He's making quarterly deposits. $1,000 quarterly. And so for 10 years, he's going to be making a total of 40 quarterly deposits. So I'm going to treat this as my annuity. And this is an annuity that has N is equal to 40 deposits in that 10-year time period. So we've got 40 quarterly deposits in that time period. The interest rate, you will note, is compounded semi-annually. So there's a conflict right there. The fact that the interest rate is compounded semi-annually but the deposits are quarterly is not a big deal for your calculator to handle this. You just have to make sure that you recognize that the interest is compounded with a different frequency than the payments are made. In addition to that, after the 10 years has gone by, Barry decides to make no further deposits. So he's going to let the money earn for interest for 5 more years. So what we want to know is what is his final value at the end of that 15 years. And in particular, we want to know how much interest he has earned, over the 15-year time period, which means that in order to calculate the interest, we need to know how much he has at the end of that 15-year time period, so we can deduct the deposits that he put in. This is obviously going to be a 2-step problem. So step 1 is going to be to find the final value at year 10. And the final value at year 10 is going to be based on the future value formula for an annuity. And I'm going to solve this problem 2 ways. I'm going to solve it using the algebraic techniques, and I'm also going to solve it using the calculator built-in functions. And remember that for test purposes and assignment purposes, you can choose whichever method you like as long as you're comfortable with it. Doesn't matter which method you use, you're going to end up with the same answer if you follow the proper techniques. So the final value is going to be calculated as $1,000 per quarter multiplied by the final value factor, which is going to be 1 plus I per quarter. Power is 40 quarterly periods, because the N in annuities is always the number of payments or the number of deposits. We subtract 1 from this and we divide by the interest rate per quarter. Now you'll notice that I didn't put in the interest rate per quarter because I don't know the interest rate per quarter. I have to have a per quarter rate in order to use the future value formula as if it was an ordinary simple annuity. So I need to convert from a semi-annual rate to a per quarter rate, and this is where your calculator is also going to come in handy. You can also use the I convert button for that, but in this case I'm going to use the conversion factor algebraic. So in order to do the conversion factor algebraically, what I'm going to do is I'm going to take this rate, which is a compounded semi-annually, so that's 1 plus 4% every 6 months for 2 semi-annual periods, is equal to 1 plus my rate per quarter for 4 quarterly periods. So we've got 2 semi-annual periods is equal to 4 quarterly periods. And I'm trying to solve for I per quarter so that I can plug it into this annuity factor. I'm going to square 1.04 squared, and then I'm going to deduct, and then I'm going to, well, let's do the squaring first. So we'll end up with, when I square 1.04, I'll end up with well, I'll have to raise both sides to the power of 1/4, so 1.04 squared raised to the power of 1/4 is equal to 1 plus I. And so what we'll have is 1.0198 and a whole bunch of other stuff is equal to 1 plus I. And I need the 1 plus I factor in the numerator of my annuity factor, so I'm going to ask you to store this in memory 1. So store 1.0198 in memory 1. That translates to 1.98 and so on percent per quarter. That's the rate per quarter. So what I want you to do now is to subtract 1 from this, and so we now have, once we subtract 1, we'll have 0.0198 and so on is the I value, and I want you to store this in memory 2. So now we can recall memory 2 for the denominator, recall memory 1 for the numerator, and work out what the final value is of that annuity. So let's do that. So we've got final value is equal to $1,000 per quarter, 1.0198 and so on. Power is positive 40 minus 1 divided by 0.0198 and so on. And remember that we're going to get this from memory 1 and this denominator from memory 2 by using recall 1 or recall 2. And when you work this out, you're going to end up with a value for the future value of $60,145 and 879 and so on. And again, I'm not going to round off. This is the amount at year 10. What I'm going to do, because I'm not finished with this problem yet, is I'm going to store this in memory 3. So we're going to store that in memory 3 because we need to do one more thing to this amount. So step 2 is going to be to use the S is equal to P multiplied by 1 plus I to the exponent n compound interest factor for the next 5 years. So we have to compound interest on the $60,000 for another 5 years at the 8% compounded semi-annually. So at 8% compounded semi-annually, what will we end up with? Well, our maturity value is going to be this amount of $60,145 and 0.879 and so on, whatever that number is from memory 3, multiplied by 1.04, 4% every 6 months, every semi-annual period. And how many semi-annual periods are there in 5 years? Well, in 5 years there are 10 semi-annual periods. And so when you recall memory 3 and you multiply this by 1.04 to the power of 10, the compound interest factor, you'll end up with a maturity value of $89,030 and 59 cents. Alternately, if you didn't want to use the 8% compounded semi-annually, you could also have used the equivalent quarterly rate, the rate compounded quarterly. And if you had used the rate compounded quarterly, the formula for the compound interest that you would have used would have been S is equal to 60,145 and 879, whatever that number was, from memory 3, multiplied by 1.0198, etc., from memory 1, and that is the rate per quarter. And so quarterly interest periods would mean that we have 20 quarterly interest periods, 5 times 4. So I'd have to raise that to the exponent 20. You would end up with the same number exactly. And it's very simple why you would end up with the same number exactly. You would end up with the same number because the rates are equivalent. And equivalent rates means that you're not going to have a different future value. So 8% compounded semi-annually is the same as this the 1.98% per quarter, which is a different quarterly rate, just a little bit less than 8% compounded quarterly. It's about 7.9 and so on. So there's our algebraic solution. We're not quite done yet. We still have to figure out what the interest is. Now, if you go back to the time diagram, you can see that he's put in 40 deposits of $1,000, so that's a total of $40,000 in deposits or in principal. So he's put in $40,000 in principal over the 10-year time period, and after 15 years he's got $89,000. So money out is $89,000, money in is $40,000, and so that means that the interest then is going to be equal to $49,030 and 59 cents. So the amount of interest is simply the difference between the money in and the money out. Now I'd like to talk to you about the calculator solution. For the calculator solution with our BA2 Plus calculator, we're going to be keying in some of the input values that we have, and again we're going to refer to our time diagram. Our time diagram has really been our savior in this case. We've got the IY is 8%, so we'll key in IY is equal to, of course we'll have to remember to clear the calculator, so hit second clear TVM to get things started, but IY is equal to 8%, and then go second IY to enter in your compounding periods per year and your payment periods per year. The compounding periods per year is 2 because it's a semi-annual rate, and the payments per year are 4 because you've got quarterly payments, and PY is always payments per year. And then you can go second quit to get out, and then you're going to enter in your payment. The payment is $1,000 and the number of payments is 40. There are 40 quarterly payments. So N always refers to the number of payments. So N has to coincide with the PY. And at this point now you've entered in all the information that you need in order to compute the future value at the end of the 40th deposit. And if you compute the future value, your calculator will give you a future value of $60,145.879 and so on. And if you wanted to, you could store this in memory 1, but personally, because this is the value at year 10, personally what I would do is I would just change the sign of that number, whatever the sign is going to be negative if you've entered in a positive here for payments. So the sign will be negative for the future value. And what I would do is I would probably enter this as now the present value for step 2. So now this becomes the present value in your calculator. So pop that into the present value now, because for step 2 what we need to do is to add compound interest to this for 5 more years. Now remember that what you've got here is in the values of your calculator, you've still got the payment set to $1,000. So what you need to do at this point is you need to set the payment equal to 0. This is key. So the payment is equal to 0. It's no longer equal to $1,000. We set the payment equal to 0. Now, how many interest periods have gone by? Well, if the interest is 8% compounded semi-annually and it's 5 years, we're looking at 10 semi-annual interest periods. However, because you've got this value inside your calculator, PY is equal to 4, you have to make sure that the number of periods is set to how many quarterly periods there are remaining in the 5-year period, for which the number of payments is equal to 0. And in that case, you've got 5 times 4, or 20 quarterly periods for which there is no payments. Okay, and everything else stays the same. You've already dropped the payment to 0. You've changed the number of payment periods from 40 to 20. And now what you want to do is you need to press compute the final value. And the final value will end up being exactly the same as what we did when we solved it algebraically. It will be $89,030 and 59 cents. And you can take it from there.